I'll be going over question 1, parts B and C from the week 6 worksheet. Part B of this question asks you to calculate the half-life of uranium-235 given an instantaneous rate of decay. We know that the rate is proportional to the number of atoms n, or the number of decaying particles. So here's your rate constant. If we can solve for that, then we'll be able to figure out the half-life. So we solve for K by plugging in what we know: the mass, the molecular weight, and Na, Avogadro's number. The mass is given as 5 times 10 to the negative 3 grams, or 5 milligrams. The molecular weight is 235 grams per mole. And Avogadro's number is 6.022 times 10 to the 23rd. And that's per mole. Mole to the negative 1. So grams cancels out, moles cancels out, you get number of particles, or unitless. Thus we can solve for K, because the rate is given. So once we have K, we can plug it into the following relation. K is equal to the natural log of 2 divided by T 1/2, or the half-life. Given that we know K, we can now solve for T to the 1/2 because the natural log of 2 is a constant. And we get the following answer. T to the 1/2 is equal to 6.16 trillion hours, or a little over 700 million years. And so there's the half-life. Part C in this question asks you what uranium-235 decays into. You're told that uranium-235 decays through alpha radiation. So the thing to remember in nuclear chemistry is that subatomic particles are conserved. So 92 protons and a total mass of 235 has to be conserved. An alpha particle is a helium nucleus. So it has 4 total particles, 2 of which are protons. So subtracting 2 from 92 and 4 from 235, we get 231 as the mass of this element, and 90 to be the atomic number. If you check your periodic table, you'll realize that 90 corresponds to thorium. So uranium-235 decays into thorium-231.